What's up, everybody? This is Matt Brown with another IoT hacking video. Today, over on my workbench, I have the Contec CMS8000 patient monitor. This is a device that is used in hospitals to monitor and alert on patients' vital signs. It is very critical that there are not security flaws in this, but it has recently been the center of controversy over whether or not there is a Chinese backdoor in this device. So we are going to discuss that in this video, and then we're going to take a look at another claim that it is sending data in an insecure way, potentially to a server locally, potentially to a Chinese server. We're going to talk about that, and we are going to decode that binary protocol and show how we can extract clear text patient data that we see on the screen over the network. And so this is going to be a fun reverse engineering exercise, and we're going to get to just dissect some of the claims made by the United States government and the CISA agency. So first, what I want to do is I want to get a second opinion, because they have written up their claims that there's a backdoor. They even talk about how, the team determined that the functionality was unlikely to be some kind of mechanism that was, it was just a simple mistake, right? And they actually think that this is intentionally. This is an intentional backdoor placed by the device manufacturer for malicious purposes. And the guys over at Claroty, if you do not know them, I'm going to drop a link to this blog post in the description of this video. They have another opinion, as you can see here, that the situation is more complicated, and I'm going to give the TLDR of this article. Their conclusions are that there's some pretty serious evidence to suggest that it is not an intentional backdoor because of how dumb it would be, given some of the things that they found in the manual, right? So right here in the operator's manual, and I have a hard copy of it here too, it mentions this Chinese IP address here. It tells you that the server IP is 202.14.4.19, that this device is trying to potentially connect back to. And they dig into this, and what they really say is that this is really just poor security, and that they're actually telling you in this manual to set up a local network, but within that local subnet, to have the subnet be this publicly routable set of IP addresses, which is not a good idea. It doesn't make any sense. Why wouldn't you just use a non-routable IP address? But their conclusions are pretty convincing to me that this is not a backdoor in the firmware update mechanism, and they do a bunch of stuff to pull the chip off. Stay tuned and definitely hit the subscribe button, because we are going to perform this firmware extraction via taking this chip off the board as well. But in this video, I want to dig in to this other thing they talk about down here a little bit. And this is the binary protocol that they see in Wireshark when they pretend to be this other server, this Chinese IP address. And so we are going to recreate that today, and then we're going to go a step further, and something I didn't see in the CISA article released, and this blog as well, and just a little bit more of decoding the binary protocol, and specifically the vitals here. So we're going to take a couple of vital signs here, and we're going to try to decode those inside of the packets we see actually going over the network, and we're going to prove that they're not encrypted, that there's no authentication happening, right? You can just, if you can set up a server and pretend to be this, or if you have man in the middle and you can see the packets going by, you're going to be able to get all of that patient data, which is not good. So what we're going to talk about first is our setup. And I have talked about this on the channel before. This is man in the middle router. I'll put a link in the description. I did not do anything genius here. I'm just taping together different open source Linux utilities. We're going to plug our IoT device into an Ethernet interface. That's going to show up on the Bro interface or Bridge 0, and then we're going to be able to sniff that traffic. So What we're going to do though is we're going to set that up a little bit different because of the unique network situation. So this device, it has a hard-coded IP address of 202.14.4.115. And the server that it attempts to reach out to is .119. And so what we want to do is we want to set up a situation where this box thinks that it's on the same subnet, the same layer 2 network as our Linux machine here. And so that's what this is going to do for us in man-in-the-middle router. And then all we're going to do is we're going to set the subnet again to be a /24. And then this DHCP range, we're just going to put it out of the way of those two IP addresses, so we're not getting any conflicts on the network. We're not really using any DHCP here because again, it's a statically assigned address on this device, and we're already running that here. And then if we come over to Wireshark, I'm getting packets, and we're going to watch what happens when we take a packet capture. We don't actually need to reboot the device today, but what we are going to do is we're going to set up this fancy view so we can see everything that's going on, because this is going to be helpful when we start to decode data. And so there you can see you can see a couple things on the screen. You can see down here is the hardest thing to read, but there's T1. There's a temperature sensor, so I have this like skin temperature sensor here. I can hold in my hand. I can see this number go up, and later we're gonna mess with the pulse ox stuff up here. But first, I want to go and look at the network packets and see what's going on. So here we see a lot of connection attempts from that 115 address. So that's the patient monitor. It's connecting to 119. So that's us. That's our Linux machine here, and it's trying to connect to port 515. Now what's interesting about that port, and this is a huge rabbit hole that led nowhere that I went down, is that's actually commonly reserved as a printer port. It's an old school printer protocol, and this like they are not using that protocol at all. Even though they're using that port, they're absolutely not using the printer protocol. But what we'll see in Wireshark when we start to sniff this data is that it actually will, like Wireshark will try to interpret the packets as this printer protocol, which really threw me off at first. I should have just looked at the raw data. So, but we can see that a reset's getting sent back, and that's because nothing on our machine is listening on this port. So we're going to come over here, and first all we're going to do is we're just going to set up netcat to listen on port 115. And we're going to have to run that as root because any port below 1024 is a privileged port in Linux, and yeah, all that stuff. So what we're going to do, and I'm just going to feed this into a hex editor, and that should start getting data flowing in. And then we're going to see a very similar set of data show up down here in our PCAP. And so what I'm going to do here with this TCP stream is I'm just going to find one of those TCP packets, and I'm going to right click on it, and I'm going to click follow TCP stream. So here we're going to get that very similar kind of view that we got right up here in the article, right? We see this similar pieces of data, and if you're wondering what these are, so it's kind of hard, I can't make this bigger. So this says C889DD. So that is a piece of clear text data among some other binary data. And so if we look over here on the patient monitor, we can actually go to menu, and then we can look at patient setup. And there you can see, yeah, you probably can't see that because here, let's go to the desk view. There we go. We can see right here that that is, you know, related to the department, patient number, bed number, doctor, identifiers there. That data is getting sent in clear text. Very obviously, we're gonna exit out of that menu. So it's pretty clear that that data is getting, exit out of the other menu. There we go. So it's very clear that from the get-go that this patient data is getting sent in the clear And that's what they talked about in both those articles. I want to go a step further, and I want to find the actual other pieces of data, like this temperature reading down here, and then I have this pulse oxygen thing right here. And so what we're going to do is we're actually going to capture that right now. So we have our little, fake server running here. And so we got the PCAT. And so I have to wait for it to get like a full set of readings. And then I should get numbers up there. Okay, cool. 74.99 or 73.99. Awesome. But 99 was a constant number that I saw there. So I'm going to hit stop on my packet capture. And I'm going to come down here, and then I have to tell this thing to silence because it detected that, oh no, the patient disconnected the device. All right. So here we go. Let's look at this packet. Let's see if I can find the right thing. All right. Gonna make sure I'm dealing with a good packet here. I am. All right. All right. Yeah. So this is gonna be a great packet for us to look at. All right. Gotta make sure. All right. Sweet. So let's go right here. Go follow TCP stream again. And actually, let's just zoom in on this right here. So here we can see a bit of this data packet. And what we're going to do is we're going to look through here for that value. And we can do this in Wireshark, but I'm actually going to start to develop a Python script, and we're going to walk through this together. And this was my process that took way longer than this video is going to be. But we're going to look through all this data, and we're going to try to find kind of like the needle in the haystack here. And so we found that value 99, right? So we know there was a 99 reading somewhere. So if we, come over here and we stop that server, let's just open Python. And what is 99 in hex? It's 63. All right, so now what we can do is now we can start to look through here for a 63 byte. And I kind of know where to look, and I need to find it. Aha! So right down here, we see a 63 byte. Now, obviously, we'd have to narrow down some false positives, but here I see 63, and then I see a 0, and then I see a 4A. And a 0. Well, that's interesting. What is 4A? So let's do that the other way. Let's say what's that in an integer? 74, and I think that's what we saw at one point up here for my, not my pulse ox, my beats per minute. So my pulse. And so those are starting to look like those binary values. So what we're going to do here is we're actually going to code a Python socket server to listen on port 515, and then it's going to receive these data packets, and it's going to start to parse them. And so what I have written so far is this is just very basic Python socket code. So we're setting up a TCP socket, we're setting this thing so it's not annoyed when we want to constantly kill the program and recreate the socket. We're going to listen on port 515. We call the listen, or we're binding, and then we're listening, and then we accept connections. And once we get a connection, it will start to receive packets. And so what we're going to do here is we're just going to print out, let's say packet.hex, and then let's surround this with just something that's going to make it easy for us to see where the delineation between different packets is. There we go. And so now we're going to run our little program here. And again, we're going to have to run it as root because we're listening on port 515. So there we go. That data is rolling through. And I'm going to once again take a reading. And then we're going to get ready to control C it once we have steady data. There we go. Okay, 85 and 98. 85 and 98. Okay, what do we want to look for? An 85 and a 98. Awesome. Patient monitor. Silence. Okay, let's open up our little, actually here, we can sneak a little Python terminal over here. And all I'm going to use this for is for math things. So 85, again, we just want to do hex of 85 right there. Okay, so we need to look for the 55 byte. So you'll notice that what we saw in Wireshark, and we're going to see here too, is that it actually sends, like, it's sending a packet, it's sending like one packet and then another packet kind of really quickly. And that's happening every second or so. And so we can really easily start to see that some of these packets start with DD, and then other packets start with 38. And so what we're gonna do, actually, so we're gonna kind of show, like, for reals how I do some of this reversing. Some of this is really funny and sketch, but I will open Vim and I'll copy all this binary data here in this packet. So what do we need to look for? We need to look for a 55 byte. Well, there we go. So we see here, we see a 55, and then it is, after it, there's a 00. Now, there's also a 00 before it. I'm just going to say that I know that this is sometimes not a 0. So I'm just gonna speed us ahead and give us that hint. So here we have that 55, and then what do we have here? We have 62. Oh, we have a 62 actually ahead of this. Well, what's 62? Let's go back, because I'm guessing it's that other number we're looking for. Hex. Boom, there we go. Okay, so so now we've found these two pieces of data here. And so again, let's just make this nice and big. So what we want to do is we want to find the offset of this first piece of data here. And you'll notice it goes 62 and then 00, and then 55 and then 00. And this is a 2 byte. Each of these are 2 byte values, but usually you would expect it to be flipped if it was little endian. But since these are bytes traveling over a network, typically network byte order is big endian, which means the littler part is at the front. And so what we want to get is the offset here. So we are going to, again, just going to open up our little Python shell, and we're going to say length of this string divided by 2. And there we get 322. And so that is the offset to get us to this byte right here, this 62 byte. So what we're going to do is we're going to come over to our script, and we're going to start adding some cool little stuff to our Python script. And so what we're going to do is first we need to go up here, and we're going to import the struct library. And that's going to help us do a bunch of data parsing over multi-byte little data types. And so what we're going to do first is okay, so we have to remember what is the order. So which one of them was first? The 62 was first. So that is the higher number, which is, no, I actually got that messed up. No. The 62 is first. 62 is this number, which is the pulse ox. Okay, so we're going to say pulse ox, which is called SPO2 here. We're going to set this equal to, and then we're going to use this cool struct thing, and we're going to say unpack. And then we are going to do this, which I'm going to explain in a minute what this means. But for now, I'm just going to write it. And then we're going to only take part of the packet. And the part of the packet we're going to take is 322 colon 342, because we're slicing that packet data down to just those 2 bytes. And when you do slices in Python, the first indice is inclusive and the last in the ending is exclusive. It doesn't include this byte at the position 324. So it's actually just taking 2 bytes, the byte at 322 and the byte at 323. And so we're going to do that. And then we're additionally going to also, at the same time, parse. Wait, do I have that? Yeah, that looks like a good line of code. All right, we're getting rid of this so we can see our stuff. And then we're also, because the beats per minute is right after that, we're also going to go and parse that next bit there. Because again, here we're talking inclusive slices, and this is exclusive. Now, what is this? So we can see that if we go to like Python struct. So this is a very cool thing, which lets us parse a lot of different common data types. And so here is this fancy little table that says an unsigned short, which is a 2-byte integer, is specified by this h value. And then there's the angle brackets. So what the angle brackets are doing is they are specifying the endianness. So we're going to specify, we're going to specify little endian, but that doesn't seem right. Actually, I think we want to do this. Well, let's experiment. All right. I think, okay, it seems like it should be like this. We're gonna find out. I don't know if that documentation is actually correct, or if I'm not understanding something correctly, because my code over on this other screen doesn't. It makes me think this is not going to work. So okay, but we're parsing these 2 values, and then let's print them out. Let's assume that we're going to parse these correctly, and so we're going to say that SPO2, comma SPO2. BPM, there we go. All right, so we're going to start this up again. And it's going to connect. Unpack requires a buffer of 2 bytes. Whoa. That's interesting. And it doesn't like me. Okay. Why does it not like this? 322. That looks good. Yeah, this is funny. Why isn't it working? Let's change this back. We're just running hypotheses here right now. Oh, that's right. I forgot a critical piece of code here. So right now, every packet, we're trying to parse every packet and find something at this really high offset. But we forgot that only the first time we get this packet right at the beginning that gives us all that, patient data and stuff like that. And that is a lot smaller of a packet. You'll see here. Yeah, like this packet is only like what, 1, 2, 3, 4, 5, 6, 7 bytes, right? So we want to find one of these packets and see every one of them, like we were talking about right here. It has the first byte of 38. And so all we need to do is to put all this stuff in here. We can say if packet at spot 1 equals 0x38, then we do all our analysis. Otherwise, we don't care right now. That's what our problem was. Haha. Now, learning things on the fly here. All right, cool. Oh yeah, I forgot those are tuples. I have to like do like array spot 0. But we can see that we're matching what we see on the screen. That's awesome. So now we're parsing the data for the SpO2 reading and the beats per minute. That is really cool. So we're going to do one more field, and this is a fun one. And I'm going to tell it to silence. That's really annoying. And so it's kind of hard to see. You're just going to have to trust me down here. Maybe we can switch to the desk cam really quick. Aha, there we go. You can see that this says temp T121. So that is this little skin temperature sensor. So I can hold it with my fingers and it will get bigger. So that is kind of cool. And this is going to be a little bit of a challenge because that is a floating point. That's not going to be as easy to decode as a straight up integer. And so what I want to do is I want to find, again, it's going to be in this same packet. You can just believe me. I've been reverse engineering this for hours. And so let's let this stabilize actually. Okay, so 25, okay, so 24.9, okay. Because what I want to do is I want to get that temperature to stabilize, and then over here, I'm going to hit Control C, and we're going to be able to find, and we're going to be able to find the float inside of this data somewhere. So, okay, I'm going to hit Control. When it goes to 24, okay, I stopped it. We're coming over here. So 24.0. We want that to be a float, and so what we're going to do to find out what that should be is we're actually going to come over here and use CyberChef. So if we want, something to be 25.0, and we can say, float. Oh, really? Does it not like that one? To float. Okay, this is really funny because I just switched to a different CyberChef and it's not acting the same way. That's so dumb. CyberChef, because, let's use this one. Who wants my data? Yay. Oh, this is the one that works. Okay, 25.0, float. Yeah, so we're going to change it to a float. And then what I want to do... Wait, no, I want from float, right? Yes, I want from float. And then I want to say to hex. So here is what the floating point number should look like in our data stream. So 41 C80000. So let's look for a 41 and a C8 in our binary data. So 41, unless I Control C it too fast, which is always possible. There's 41. There's 41 C0. I think I Control C it too fast. So what we're gonna do is we're gonna kind of cheat. Okay, so we see the 41 at the end. I have a hunch that this is it. So if I Control C it too fast, then the temperature would have been higher than it was. So it would have been like, or no, it was like 24.9. Okay. There's that. 41, C1, 99A1. Okay, yeah. So I think this will actually serve us really well. Oops, wrong way. Okay, so this is potentially, 41. Okay, let's like put this in and let's do it backwards. I think this is it. So we're going to say from hex, and then we're going to say to float. Oh, I'm doing it wrong. Big Indian, little Indian. Ah, there we go. We found it, guys. All right. So our offset is 1, 2, 3, 4. We can just count it from the top. 5, 6, 7, 8. Okay, so there it is. 8. All right. So now we're going to just call it T1, temperature 1, struct unpack. And we're going to say, you know, there's our Indian flag, F, comma, packet, and our offset is going to be 8, and then we're going to go 4 bytes, so 12. So there's our packet, and we are going to print out T1, our floating point value. Oh yeah. Here, we're gonna kind of fix this up. We're gonna have it not print out in that tuple format. There we go. All right, here we go. Starting it. And I'm going to hold on to the temperature sensor, and we're going to have the pulse ox on. Awesome. 26.5. Yep, looks good. It's heating up. And now we have our other values. So now we can capture all 3 of those values. And there are certainly others that we could reverse engineer in the same fashion, right? I could hook up all of the other probes and stuff like that, and we could figure out where in the binary protocol the offsets for those data fields are. But I think that's pretty good to show us that we are able to write a program that's able to completely parse this data and act as this server. And this kind of a server is potentially what that Chinese university could set up to capture data where these devices have been misconfigured and have access to the internet, and the routing is such that they actually will get routed out to the internet and properly routed back over here. Again, it might not happen that way in reality, but this is a huge risk. And again, they are telling people to set up these systems inside of the hospital. So if an attacker was on the local network at the hospital, they would be able to see this data, and it's not secure. If you have one of these devices, honestly, if you don't have remote monitoring on it, just unplug the Ethernet and don't use the Wi-Fi, right? Like, that's probably the best solution for this device. Definitely don't follow their terrible advice on how to configure it in the manual. But I hope you saw in this video how the process of reverse engineering these binary protocols is slow sometimes, and sometimes you take like a couple steps forward and a couple steps back, right? I went down the rabbit hole of thinking it was actually using that printer protocol that we saw it be decoded as in Wireshark, right? So when you're reverse engineering these custom protocols, these binary protocols, you're chipping away and you're gaining a little bit more knowledge and a little bit more knowledge. You're testing hypotheses, you're ruling them out, and eventually you get to a really cool result. And the other thing you have to remember is that you don't have to decode everything, right? I didn't write a decoder that decoded everything in that packet. I just decoded really interesting data that I wanted to get out of the protocol. So thank you for watching this video. If you like this kind of content, please subscribe, because it really helps me to grow the channel and to make more awesome educational content for people like you. And if you're a company and you're watching this and you need a device pen test, please consider Brown Fine Security. Have a good day.